So next we need to look at operations on arrays. And okay, so we're starting out. What sort of operations do we want to do? What's going to be useful for us with an array? Well, we've been talking about the simplest one already. We've been talking about read and write. Okay, so code for getting a slot from an array is super simple. We've been doing this for a while, right? Array name index. So A of 4 or current name, names of current index, right? It doesn't have to be an explicit literal. It can be a variable, an equation, a function, whatever. Okay. And we just established that reading from a given slot is real quick and easy. So, like I said, accessing that memory address is big O of 1 because it's just running that calculation. And the same can be said for writing into an empty slot, right? Writing into an empty slot or overwriting a slot with a value, if the slot already has data in it, which, pro tip, arrays have data in it even when declared. Computers don't zero out the data in memory, okay? Some languages will mask the data that's already there, but there's no point in zeroing it out. Of course, unless a hacker knows what's going on, asks for a big chunk of memory that it can then just read the data in and hope that sensitive information's there. This does happen in certain low-level languages. This is a risk in something like C, okay, which Python is built on, but Python hides that stuff from you. So writing into an empty slot, writing into a slot with a value is no different than just storing data in a variable. It's no different than saying x equals. So this is also big O of 1. So that's great. That's really good. What else could we want to do though, right? We could fill a slot in. We could read from a slot. Well, what if we have A, C, D in our, A, C, B, A, C, D in our array, and we want to insert B, and we want to keep this in order, okay? Our data is ordered, and inherently, remember, arrays are dynamically sized. Arrays are not dynamically sized. Arrays are statically sized. So if I want to be able to do this, I need at least one slot towards the end of my array that I can fill in at. Well, where would B go? B would need to go here. So this process is called insertion. We want to insert data into our array without destroying the data that's already there. So let's say that we have this array, okay? And we want to insert X at index 2. So X wants to go here. So what we need to do is consider that we want to put X in between foo and 0.2. So how's that going to work? What are we going to need to do? Because we can't just put X there, right? Remember, it's not continuous. So we can't subdivide it and just magically find memory. Instead, what we're going to need to do is start at the end, start all the way out here. And since we got space back here, we can just copy a value up, right? We're going to copy each element up one slot, and then we're going to iterate down until we find the slot that we want to copy into. So 50 moves up, then 15 can overwrite 50 because we've made a copy, and bar can overwrite negative 15, and we can keep going until we get to 0.2, right? And once we get here, we can overwrite it with X because the data is redundant. We also, depending on our implementation, it's not uncommon to store some variable that's called like count and maintain a count of the number of elements in this array. Because if we said len of the array, if we said len of A, the interpreter is going to go, oh, cool, it's 11, right? Because we have 11 slots, 0 to 10. The interpreter doesn't know how many are full. The interpreter doesn't know that there are 8 elements. So we might need to increment a count variable if we're storing this data externally. So what's the runtime efficiency of this whole process? Let's think about it. In the best case scenario, if I wanted to add another element, where would I want to add it? Well, I'd want to add it in the spot where I'd have to copy the least amount of data. Well, that would be out here, right? If I add it at the end, I don't have to copy anything down. I just write it in. So that's beautiful. That's a big O of 1. What's the worst case scenario? Well, the worst case scenario is that I put it here. And now all of a sudden I have to move everything down. So as my data grows, right, as the number of elements in my list grows and my array grows, the amount of data that I have to copy down grows proportionally. So it's a big O of n process, right? Having 5 elements and inserting at the front is going to be half the time that it's going to take if I have 10 elements. Okay. What's the average case? On average, where am I going to be putting this? Okay, well, probably somewhere in the middle, right? Roughly in the middle. Well, as my list grows, for every 2 elements I add, I'm going to be adding 1 additional copy. Well, that's still proportional to the length of the data. So that's also big O of n. So we can see that here. Our best case is constant, right? This is just, one operation. Our worst case is proportional to n operations because I got to move everything down. And our average case is about half of them. Okay. What else would we want to do? What else could we want to do in this case? Well, what about the opposite? What about deleting or removing from an array? Right? The opposite of an insert operation. Grab data from a spot and move everything down. Okay. Well, what are we going to need to do? Depending on whether we want to return the element that we're deleting or not, first thing we're going to have to do is grab that element, right? Copy that element. If I want to move B out of this array, first thing I have to do is take B and store it somewhere else so that I can then, starting at that index, copy each element down a slot. So I can overwrite B with C, and then I can overwrite C with D. And then once we get to the end, once we've got no more data to move, we nuke this. We overwrite it with a null or a none, depending on what language you're using. Obviously, in Python, we have none. Other languages have null. If you're working in C, it's 0. Whatever your language uses is what it uses. And then, remember, we have that count element. So we're going to have to decrement our count. And then if we're returning our data, we return it. Well, what's the runtime efficiency of this process? Well, we've got a couple extra steps, but this is constant, and this is constant, and this is constant, right? Those are all going to be individual operations. So a constant plus a constant is constant, right? 1 plus 1 is 2. So again, right, best case scenario, we delete from the last element in our array. We only have to delete that one thing. We don't have to copy anything down. Worst case scenario is we delete from the front, and we have to move everything that's left over down. And average case scenario is we delete from the middle, and we have to move about half of our data down. So once again, our runtime analysis is big O of 1 in the best case and big O of n in the average and the worst case. Okay. So what are some benefits to arrays, right? Read and write operations are really, 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 really fast, right? Since we know the array's address, we can calculate it and we can jump to it in big O of 1. And then because we have the index for the element we want and that equation, we can jump to any element in the array in big O of 1 as well. They're also really memory efficient because an array is functionally just a bunch of variables in a row with almost no memory overhead, right? This is a slide. If you're going to take nothing else from this class, this is the information that I want you to take. Okay? This is why when you hear Dr. Shalon talking, or if you had heard Professor Rumbaugh talking, and they're C programmers, they go, why do you need objects? All you need is an array. And this is why, right? Because they're fast and they have no overhead. If you're good at what you do, you can do pretty much anything with arrays and variables and be wildly efficient. There are downsides. There's always downsides, right? Anything with a benefit has a cost. And one of the big ones is the static sizing. Okay. What happens if we iterate past the end of an array? Well, it depends. Some languages say it's out of bounds. Others rely on you to check the boundaries, right? And then if you don't, they just let you access out of bounds memory, which is not great. That's called a buffer overrun. And attackers can use that to do a buffer overrun attack to either, especially in small interconnected devices, they can know how memory is laid out and either insert malicious code past the buffer in memory where they know it'll be executed, or they can just overrun the buffer, access the data there, and hope that there's something important. If you want to see really cool, very visual uses of how buffer overruns can work, look at some speedrunners who use glitches to trigger states in 8 and 16-bit games. A lot of them are based on buffer overruns, on manipulating specific memory that you really shouldn't have access to yet, just through quirks of the game. Okay, but you can see how this could do a problem, could cause a problem. And for the record, Python throws an index error. So Python doesn't require you to check boundaries, but if you don't check boundaries, you're going to have an exception. The other issue with static sizing is what happens if we need more space? Well, we need to create a larger array. And then we need to copy the data down. And then we have to destroy the old array. Okay. Why is this inefficient? Well, think about it with respect to runtime. How long is this process? Well, we have to copy one element for every element we have. So that's a big O of N process. That's not great. And think about memory consumption. Let's think about this with respect to memory consumption. If I have 1,000,000 elements and I need 1.5 million in the array, I need to expand the array. Then I need to have enough memory for 2.5 million elements. And if I don't, even though I'm not going to keep both of these arrays at the same time, I can't do it. I need enough memory for both the original and the copy. And I have to be sure to destroy the old array. If I don't do that, it's going to hang out there in memory and just be a dead block of memory called a memory leak. This doesn't happen nearly as much in garbage collected languages, but if you were working in C, you'd have to deallocate that memory. Otherwise, it'll just hang out there for forever. So the question becomes, can we improve this behavior? And if we can't, is there a way that we can optimize it to make our lives easier? Right? Either make it as efficient as possible, or at least make sure that we don't have to manage it. And the answer is yes.